Okay, so my research presentation is going to be on discriminability and stimulus generalization. So I'm just going to provide a brief review of stimulus discrimination and stimulus generalization. They're both discussed in our book by Tom Jam. So stimulus discrimination is the ability to distinguish between two stimuli and respond differently to these two stimuli. Stimulus generalization is generally just the opposite of it, in which an individual will respond in a similar manner to multiple stimuli. So, for instance, imagine that an organism is provided reinforcement following the pressing of a white button. Stimulus discrimination would be able to sit the organism press the button in the presence of the white light, but not in the presence of a red light. However, stimulus generalization would be if the organism pressed the button in the presence of the white light and in the red light. Therefore, they exhibited the same response for multiple different stimuli. So, the article that I picked was by Gutman and Kalish, and it focused on stimulus discrimination and generalization. And it also talked about something called the difference Lyman, which is what is like a new term, but it relates to discrimination. So proposals for the formulation of stimulus generalization gradients assume that a decrease in generalization, this would be the generalization decrement, is associated with an increase in discrimination, and vice versa. So there's an equation here that provides information about discrimination as well as generalization decrement, and that is this difference Lyman equation, which DL is equals to delta L S divided by delta P times R. So what is the difference Lyman? So this is basically the smallest detectable difference between two stimuli. So how much a stimulus must be changed for it to be detected at least 50% of the time. So for instance, um, lower values of the difference Lyman mean that the organism is able to distinguish stimuli very well between one another. For instance, say they're given a wavelength of light at like 580 nanometers and they're trained at that wavelength. And then you show them 581 nanometer wavelength and they don't respond to it, but they only respond to the 580. That would mean that the DL would be like a low value because they're very good at discriminating. If DL is high, then that means that they're not very good at discriminating between those stimuli. Okay. And the generalization decrement is given by the values delta P times R over delta S. And to compare that to the above equation, that is the inverse of DL. So it's 1 over DL equals the generalization decrement according to this equation, which I'll talk about on the next slide. So there's an inverse relation between DL and the generalization decrement, kind of just like the decrease in generalization is basically the slope of the generalization gradients. So the census indicates that a discrimination leads to a decrease in generalization. Um, Gutman and Kalish assess generalization gradients using various wavelengths of light, and they will show this parameter delta lambda. When they show it, it's just equal to DL. Okay, so when I show graphs later on, I'll say it again. Delta lambda is just equal to DL, and what they assessed was key pecking responses. And they assessed key pecking responses to various wavelengths of light, and they developed generalization gradients using them. So what is the purpose of this study? So the purpose of the study is basically to like evaluate this equation. The researchers aim to evaluate the presence of a relationship between discriminability and stimulus generalization relating to wavelength and spectrum colors. The delta lambda is different for various wavelengths of light, providing a means of assessing such relationship, meaning some of the pigeons, which are the subjects in the study, are better at discriminating some wavelengths of light than others. Okay, which means that you have very different DL values depending on what wavelength you're actually testing. So the subjects and setting. So there were 24 pigeons that were experimenting naive, which means they weren't like magazine trained and stuff. They also did restricted feeding on these pigeons to 80% of their ad lib and body weight, which is like I think like if they just were able to eat, then they restricted the feeding to 80% of that body weight. They also used a Skinner's automatic key pecking apparatus and they modified it. So this is just a general operant chamber. Unfortunately, the article didn't show a picture of the apparatus, so I couldn't provide it here. So the picture is just like an example, basically an operant chamber. So the apparatus they used was 12 inches wide, 14 inches high, and 12 inches long. And there was a rectangular key that was positioned above the floor. I think it was like 6 inches or something above the floor. Okay. And then the floors were like clear with like metal grates, and the ceiling was, I think, clear as well. So the magazine, which is where food was delivered, was under the rectangular key. So under the rectangular key, there was a magazine. That's where food was delivered, and there was a metal like lid or door that would open and allow them to grab the food from it. And then they changed the color of the response key using like some monochromatic. Um, I just provided an image below of an operand chamber to just show you like basically a magazine compartment. And then so you'd have like the magazine compartment right there where the food would be delivered, and then right above it there would be a response key. Okay. Unfortunately, they don't have a picture in their article. So now I'm going to talk about the procedure. So they did magazine training, and they taught the pigeons to respond to the button using like keypecks. And they said that they used successive approximations to teach the pigeons to peck the key. That was about, they didn't provide like a lot of detailed information about how they taught the pigeons to key peck. Now, the main focus of their procedure involves the next part. So they took the 24 pigeons that they had and they separated them into 4 groups. Okay, so there were 6 pigeons in each group, and each group was taught or trained on a specific wavelength of light. Okay, they called it a CS. Also, the unit is like mu. I'm just going to call it nanometers because that's what I'm used to calling it. So like the groups we either train at 530 nanometers, 550 nanometers, 580 nanometers, or 600 nanometers. They were given 50 edible reinforcers. Each of the pigeons get 50 edible reinforcers each day for 2 days. And then following these 2 days, they did irregular, almost aperiodic reinforcement, is what they called it. That was right following these days. And there were 1 minute inter-reinforcement interval was provided. So that means there was a 1 minute period of time between the delivery of reinforcement. Okay. And so I'm going to talk about the structure of these aperiodic reinforcement sessions. So the researchers would alternate between a 60-second stimulus on interval and a 10-second stimulus off interval. So that would mean that the button response key would be illuminated with the corresponding wavelength for that group for 60 seconds. Then after 60 seconds, they would have a 10-second interval where the button would not be illuminated. They also dimmed the cage as well. And then they did 30 stimulus on intervals each day of training. So that means 30 stimulus on intervals and 30 stimulus off intervals. The stimulus on trials involve the key being illuminated with a wavelength of light corresponding to the specific group, like I just said. And the stimulus off trials involve the response key and apparatus not being illuminated with light. This was termed like blackout, so it's dark. Okay, the key was not illuminated. Following the aperiodic reinforcement sessions, they did generalization tests. Okay, but in between the aperiodic reinforcement and generalization tests, they did do something. They had 6 30-second intervals, and they would expose the groups the wavelength of light that corresponded to their group, and then they would provide 3 reinforcers for like responding during each of these intervals. Okay, so they did that immediately prior to the generalization testing and after the aperiodic reinforcement. There were also a total of 2 generalization tests conducted. I'll mention that later. So in the generalization testing, they would present the pigeons with 11 different stimuli. Okay, and you can see it in table 1. Okay, each stimulus was presented for 30 seconds, and then there was a 10-second blackout. And this was like also an extinction. So when they pressed the button, even if they pressed it in the presence of the wavelength they were trained on, there was no edibles provided. Okay, so no reinforcers were provided. And they conducted a total of 12 generalization sessions in the first generalization test. Okay, so in the first generalization test, they conducted 12 generalization sessions, and each session it consisted of the presentation of 11 different stimuli. So from the table, you can see the 4 groups, 530, 550, 580, 600. And that was the wavelength of light that those were trained on. Okay, and that's termed the CS. And you see at the top, it says plus 10, plus 20, plus 30, plus 40. That's how much the wavelength they're testing deviates from the CS. Same thing with the minus. Okay. And then, so after they did their first generalization test, they then did 3 more aperiodic reinforcement sessions, the same way that I described it previously. And then they conducted a second generalization test. The procedure was exactly the same. Okay. So they just did 2 generalization tests using these procedures. And so what did the researchers record? So the researchers recorded the number of key pecks on the response key by the pigeons and the rate of responding. Okay, both of these values. They created mean generalization gradients for each of the groups, and as well as individual generalization gradients. So you're going to see where the x-axis is going to be the wavelength, or it's like deviation from the CS versus the mean number of key pecks. Okay, there's also some other graphs that I'll talk about later when I talk about the results that are like a little more like complicated. So these are the results from the mean generalization gradients from the first generalization test. If you remember, there was two. So the figure that I'm going to talk about here, this is the whole figure. I'm just going to talk about the graph on the top to start with. Okay, the graph on the bottom was they took it from another article. They got information from another article to have that. Okay, so the researchers analyzed the generalization gradients, and for the first generalization test, many of the graphs showed or the gradients showed similar characteristics. So there's initial linearly decreasing number of responses on both sides of the CS. So they just decreased linearly. However, they started to flare out towards the bottom. So as the wavelength that they were presented got further and further away from the CS, you see it start to decelerate and flare out. Okay, that was as the responses approach zero, and you can see it in all the graphs. You can see my mouse; it's like right here on all the graphs towards the end of them as they get really far away from the CS. Additionally, Gutman and Kalish stated that the slopes of the curves were similar to one another, the change in the slopes of the curve, despite certain groups being exposed to many different spectral hues. So like the group that was trained on 600 nanometers experienced like orange, yellow, and green light. Okay, so green hues. However, there were similar changes to the slope. However, they then did statistical analysis on it, and there actually were some differences. So the primary difference between the gradients relates to the levels of responding. And then I'm going to talk about like some statistics that they did with the graph. So they did statistical analysis on it and indicated that from the CS, or the trained stimulus, to minus 480 mu or nanometers, there was no significant difference in the interaction of the wavelength of touch stimuli and CS groups. So there was no significant difference in the slopes of these mean generalization gradients. Additionally, statistical analysis from the CS to the plus 40 nanometers indicated that there was significant difference in the slopes. However, this was because there were differences in the 600 nanometer, 500 nanometer mean generalization gradients. If you actually took those away, then there wasn't a significant difference between the slopes. So the statistical analysis indicated also significant difference between the levels of the graphs. As you saw previously, like the 600 nanometer had a lot more responding. And now I'm going to talk about the graph that was on the bottom of that figure. So this graph was taken from some other article, okay? Information taken from that article, and this demonstrates delta lambda. So if you remember, I said delta lambda is equal to like the difference Lehman in this study. So what you would expect from this graph is that the pigeons would be best able to the pigeons that were trained at 580 nanometers would be best able to distinguish wavelengths of light that deviate from 580 nanometers. And the pigeons that were trained on 530 nanometers would have the most difficulty distinguishing between stimuli. And that was because the delta lambda, or the DL, is highest at 530 and it's lowest at 580. So you have a trough at 580 and a peak at 530 with regards to the difference Lehman. And as I said earlier, if the DL is low, that means that they're going to be better able to distinguish stimuli. Okay, but if it's high, they're going to have a harder time differentiating stimuli. Okay, and so then how does this relate to like the data? So if you look at their mean generalization gradients, you would expect that the steepest slope would be displayed in the group with the CS being 580 because they're best able to discriminate according to that other graph. And the flattest slope would be displayed in the group with the CS being 530 because they would have the most difficulty discriminating the group that was trained at 530 nanometers. However, this is not what was depicted in the mean generalization gradients. The group that was trained at 580 nanometers had the flattest slope rather than the steepest slope, okay, which is not what was expected. Now, remember I said previously that the graph that I showed you last time was the mean generalization gradients for the first generalization test. Now this is the graph for the for the second generalization test, okay? This is the mean generalization gradients for the second test, okay? And they were very similar to the mean generalization gradients from the first test. They were essentially just like proportionately smaller versions of those from the first generalization test. I'm going to show you another graph. They basically summed up all of the like responses from the first test and then summed all the responses from the second test and then just made a giant generalization gradient. And as you can see, they're proportionate to one another. The second one is just basically smaller version of the first one. I guess they want to see like replicability. You would want them to be like proportionate to one another. Otherwise, there'd be, I guess, some issue with how you did it the second time. So the researchers also provide individual generalization gradients, which is what I said earlier, for 3 pigeons in each group. So at the top you see is 3 pigeons at 530 nanometers. Second is 3 pigeons at 550. Third is 3 pigeons at 580, and the last one is 3 pigeons in 600 nanometers. Okay. Um, and so what they saw basically was that if you compare the first generalization test and the second generalization test, they were similar to one another. The second generalization test is shown by the dotted line, and the first is shown by the solid line. Okay. It basically, the first one, just like I said previously, looks like a bigger version of the second one. Okay. For most of them, there are some differences. And then they also stated that the individual generalization gradients did not always were representative of the mean generalization gradients, which I guess you would expect. You could have like some outliers in the individual generalization gradients. So now they did something else. This is when I'm talking about the other graphs. That was a little bit more confusing. So they took the response strength of the pigeons and they separated them into groups based off of their response strength to the first generalization test. So the pigeons were separated from their respective groups. So the groups are now no longer, they're like 550, 530, 580, 600 nanometers. Okay. They're placed into groups depending on the number of responses. So their response strength. So you see 3 groups. It says lowest third of subjects, middle third of subjects, highest third of subjects with regards to the number of responses that they emitted. Okay. And they noticed that as the number of responses decreased, the generalization gradients became flatter and flatter and flatter. Okay. And now they did this same thing again, but rather than response strength, they did it with test series. So if you remember, there were 12 total sessions in the generalization test phase. So they basically took the results from the first 3, made that one group. The results from the sessions 4, 5, and 6 made that another group. The results from 7, 8, 9 made that a group. And then results 10, 11, 12 and made that a group. Okay. So they took all the pages and made them together. They just separated the groups based off of the data from like the sessions from 1 to 3, of 4 to 6, 7 to 9, and 10 to 12. I hope that makes sense. And they noticed that as the generalization test progressed, which remember was an extinction procedure, the generalization gradients became flatter, which I guess you would assume because they're implementing extinction. So you would think they would start getting flatter as you progress in the generalization test. So the last graph is that they developed a visual depiction of information obtained from the generalization gradients that were determined from the previous 2 graphs I showed you. So the one where they separated the groups in response strength and the one where they separated the groups into like different generalization based off of like the different series in the generalization sessions. Okay. So basically there was a clear similarity between the groups separated based on level of responding and groups separated based on generalization test series. Okay. So you can see that here. You see like there's CS plus or minus 10 nanometers, plus or minus 20. And if you look at the graph, you see that the dotted line is showing you when they separated the groups based off of their generalization test series, and the solid line is when they separated the groups based off of their response strength. And the lines are like corresponding to one another, very close and very similar to one another. Okay. So now you're thinking like, what exactly does all this information mean? So what I got from the discussion section is that there's also some experiment indicate that there may not be a correspondence between the generalization process and the discriminability function for wavelength of light, okay? Which they, in their hypothesis, they expected there to be one, okay? So the current results did not support the previous equation that I presented earlier with regards to like generalization decrement and difference Leman. The generalization gradients were flatter than would have been expected by the discriminability function. So if you notice, I mentioned previously that at the 580, the pigeons that were trained at 580 nanometers, they were supposed to have the steepest generalization gradient, but they ended up having the flattest. That doesn't correspond to their hypothesis. You would have expected the flattest to be at 530 nanometers, where the pigeons were shown to have the most difficulty distinguishing between stimuli. Okay. And then additionally, they stated that maybe the relationship between discriminability and generalization is not as simple as previously proposed. So maybe it's actually more complicated than people previously thought. Maybe it's like, obviously, as you increase discrimination, you will decrease generalization, but maybe it's more complicated than just being inversely related to one another. And then they just mentioned some brief limitations of their study. One of them was that there may have been potential variations in brightness when presented with the keys. So maybe some of the illuminations for one group is actually a little bit brighter than another. Additionally, they said that the pigeons were in dim light when they conducted the study, and this also could have impacted the rate of their responding and the number of KPECs. So this is my general discussion. So I'm just going to review what I said. So the researchers conducted a generalization test on 4 groups of pigeons after training them to engage in KPECs in the presence of wavelengths of light that were specified for each group. Okay. They also used the Diffrin-Lehman equation, and they assessed the Diffrin equation to determine if there's a relationship between the discriminability function for the wavelength of light and generalization, which the results said that there was not. The research acknowledged that there obviously is a relationship between discrimination and generalization, but the process may be more complicated than was previously believed. Now, these findings are, I think, valuable because they do provide more information about stimulus discrimination and stimulus generalization. And future researchers can certainly continue to assess this to try and demonstrate a relationship between the discriminability function of the wavelength of light and generalization. And if you continue to do studies on this, it might provide you with information about how to predict generalization gradients and basically how different 2 stimuli need to be for an organism to be able to actually distinguish those stimuli. And then I thought was interesting, I thought this could be expanded like the people. So then you assess it with like people and certain stimuli with people. And then you could compare how individuals with autism and individuals that aren't diagnosed with ASD have differences in their Diffrin-Lehman, or see if there are differences. Do the stimuli need to be very, very different from one another for individuals with autism to actually be able to distinguish those stimuli? And is that more than individuals that aren't diagnosed with autism? Okay. Like, are individuals that aren't autistic better able to distinguish between stimuli than individuals that are autistic? So the researchers also they also mentioned this at the end, so I just want to bring it up. They discovered similar changes in the generalization gradients when gradients were assessed with regards to response strength and generalization test sessions. Like I mentioned previously, the results indicated a combined multiplicative and additive relationship, or some like statistical thing with equations. So I'm going to also mention again what I talked about future research. Future research should continue to assess relationships between discriminability and generalization, and future researchers may also want to reevaluate the procedure by requiring their participants to make a comparative judgment. So this is a critique I have of their procedure. During their generalization test phases, they would just present one light. So it would just be whether like the CS or any deviation from it, rather than 2 lights. So they could have had one light be the actual trained response, like trained light, the CS, and then the other response key being the one that deviated from it, and then seeing which ones the pigeon selected. Okay, that might have been more effective than just using one light. So additionally, future researchers can also compare generalization grades for different stimuli. This is what I think is like actually really interesting. So for instance, if you expect an organism to be better able to distinguish stimuli, like wavelength-based stimuli like light, compared to like tones, then you would expect a steeper generalization gradient or a tighter generalization gradient when they are distinguishing between wavelengths of light compared to when they are distinguishing between tones. And now, so this is my critique. So my critiques are for the article itself. I did have to remember the article was written in 1956. So one, there was no abstract in their actual article. Okay. They also didn't really describe the parameters of the Diffrin-Lehman equation. Like what delta P times R meant or what delta S meant. They didn't really go into detail about that and did not describe it very well. I also didn't like there was no visual depiction of the apparatus that they used. So you just kind of had to imagine it from how they described it. And I think a separate section describing the dependent variable should have been incorporated into their article. Now, this was written in 1956. So now for the procedure itself, one of my biggest things was that there weren't two stimuli that the organisms were selecting between. They just showed them one. So they trained them on the certain wavelength of light. And then during the generalization test phases, they just had one key illuminated, either illuminated with the CS or any deviation from the CS. Maybe it would have been better to have 2 response keys and they had to select between them. One being the CS and then one being the one that deviated from it. I think that would have been maybe that would have been different results, would have been more effective. Maybe they would have seen a relationship. Also, they conducted fewer aperiodic reinforcement sessions prior to the second generalization test than the first generalization test phase. Remember, there was only like 3. prior to the second generalization test phase, and I wonder if this could have impacted their results in some way, even though the second generalization test phase, those generalization gradients were just smaller versions of the first one. I do wonder if it did matter a little. So these are my references, and that's it. Thank you.